Are you struggling with cracking in your nickel superalloy parts made using additive manufacturing? If you're looking to boost the quality and reliability of your metal prints, you've come to the right place. In this video, we'll uncover practical solutions and best practices that can help you minimize cracks and defects in nickel superalloy AM parts. Stick around to learn how to take your additive manufacturing process to the next level. Welcome back to our channel. In our last video, we explored the root causes and types of cracks commonly found in nickel superalloys during additive manufacturing. Today, we're shifting gears to focus on actionable solutions and best practices to effectively minimize these defects and enhance the quality of your AM parts. Let's dive into the key strategies for reducing cracking in nickel superalloy components. The first line of defense against cracking is optimizing your AM process parameters. Fine-tuning the energy input from the laser or electron beam is crucial for managing thermal gradients and residual stresses. Parameters such as laser power, scan speed, hatch spacing, and layer thickness directly influence heat input and cooling rates. Achieving the right balance for each specific alloy and part geometry often requires a mix of experimental trials and advanced simulations. Preheating the substrate before the AM build can effectively reduce thermal gradients and residual stresses. The higher the preheat temperature, the lower the thermal gradient, which minimizes the risk of cracking. However, it's important to find an optimal temperature that avoids unwanted grain growth or changes in material properties. Using advanced scanning strategies is another effective way to control heat distribution and solidification patterns. Moving beyond traditional raster or zigzag patterns, methods like island scanning, contour scanning, or fractal scanning can disrupt continuous melt pools, reduce thermal gradients, and promote more uniform grain structures. These techniques significantly lower the likelihood of cracking. Modifying the laser beam's shape and intensity can also help manage melt pool dynamics and solidification behavior. Techniques like beam wobbling, modulation, or using a wider or elliptical beam shape can create a more even heat distribution, lower peak temperatures, and reduce the formation of microstructures prone to cracking. Adding nanoparticles, such as ceramic particles, to the nickel superalloy powder feedstock can refine the microstructure and enhance cracking resistance. These nanoparticles act as nucleation sites during solidification, promoting finer grain structures and reducing crack susceptibility. However, finding effective and commercially available grain refiners for nickel superalloys remains a challenge that requires further research. Customizing the composition of nickel superalloys specifically for additive manufacturing is a powerful way to enhance crack resistance. By adjusting alloying elements, you can narrow the solidification range, reduce the formation of low melting point phases, and improve the overall resistance to cracking. This approach, known as alloys by design for additive manufacturing, is an active research area requiring advanced computational methods to predict the effects of compositional changes. Proper heat treatments after AM can relieve residual stresses, homogenize the microstructure, and improve mechanical properties. High-temperature solution heat treatments, followed by controlled cooling, can dissolve unwanted phases and achieve a more uniform distribution of strengthening precipitates. However, high temperatures can also lead to grain growth and distortion, so optimizing heat treatment parameters is essential for each alloy and part geometry. Hot isostatic pressing is another effective post-processing technique that involves applying high pressure and temperature to the AM part in a controlled environment. This process can close porosity, heal internal cracks, and improve the overall structural integrity of the component. However, HIP is expensive and time-consuming and may not be suitable for all nickel superalloy compositions or part geometries. By integrating these process control techniques, material-specific solutions, and post-processing methods, you can dramatically reduce cracking in nickel superalloy AM parts. Remember, success in additive manufacturing requires a deep understanding of the specific alloy, desired part properties, and the capabilities of your AM equipment. If you found this video valuable, make sure to hit the like button, subscribe to our channel, and ring the notification bell so you never miss our latest insights on metal additive manufacturing. And don't forget to share this video with colleagues who might benefit from these strategies. Thank you for watching, and stay tuned for more expert tips on advancing your AM processes.